on the inside. So you're never taking the square root of a negative number. That's one reason why, right? Because this is squared, right? So it's not going to be negative. And then also, the odd roots, you know, if I ask you, the odd roots were actually allowed to take the square root of a negative number. What's the cube root of negative 1? Negative 1, right? Negative 1 times negative 1 is 1, but times negative 1 more time is negative 1, right? So that doesn't have a problem, actually. So cube roots don't have that problem. Okay? So anyway, those are the two things you have to think about. Are you dividing by 0, and are you taking square roots of negative numbers? Okay, let's see what they say here. How to do this.
Find the exact location of all the relative and absolute extrema of the function h of x equal to the quantity x plus 1 to the 2/5 power with the domain the closed interval from -2 to 0. The endpoints are -2 and 0. To find any stationary points, we take h prime of x, which follows from the generalized power rule, and is 2/5 the quantity x plus.
Okay, so they do something called the generalized power rule, because this is something raised to the power, and then we have something inside, right? So it's like the power rule, but we have a more complicated thing inside, but I don't bother to do that. I just say this is the chain rule, because the generalized power rule is just a part of the chain rule. So I don't call it the generalized chain rule, but they often call it the generalized power rule, but they often call it the generalized power rule. Okay, but it's the chain rule. It's just the chain rule. So what would we do here to get to do the chain rule? It would be 2/5 times this to the what? You have to subtract 1 from the exponent. So it's, what does that become? 2/5 minus 1 is what? 2 minus 5 is what? -3. So it's -3/5, right? Okay. And then you have to take the times the derivative of the inside, which is just times 1. Okay, so that's all. That they call it doing the generalized power rule.
It's 1 to the power -3/5, or as a rational expression, 2 over 5 times the quantity x plus 1 to the power 3/5, and set it equal to 0.
Okay, now the derivative might have a problem because we might be dividing by 0, right? The derivative. So the derivative might be undefined at certain places. Okay, let's see what they do.
Now we solve.
Okay, so what's the answer here? What are they doing here? They're setting the derivative equal to 0. Why? What are we trying to find? The local or relative extrema, right? So we set the derivative equals 0. But what about here? What about in this case? Is the derivative ever going to be equal to 0? It's 2 over something, right? That's not going to be 0, right? Because the denominator is a constant, it's not 0. Okay, so we're not going to have any, what? Relative extrema. Okay?
It's impossible to solve, so there are no stationary points. So we just check the value of the endpoints and the one singular point.
Singular point.
We can't.
So the singular point is where the derivative is not defined. And what about this? So if x equals -1, we get 0 in the denominator, right? Okay, so that's going to be a singular point.
And make h prime of x undefined if we set x equal to -1. So looking at x and h of x, when x is -2, h of x is 1. When x is -1, h of x is 0.
Okay, what's he doing now? What's he doing here? Said when x is equal to -2 and when x is equal to -1. And what's the other point? When x equals 0, right? So we want to check the height of h, not the derivative, but actually, the question doesn't actually ask that, it just asks where they are. But anyway, let's see. So he's checking at what is h when x is -2, what is h when x is -1, which is the singular point, and then what is h when x is 0?
When x is 0, h of x is 1. Taking a look at the graph, we can see that the endpoints are absolute maxima, and the cusp is the absolute minimum. The absolute maxima are located at -2, 1, and 0, 1. And the absolute minimum is at -1, 0.
All right. Let's try. Let's see what else is there. So here, by the way, they want you to go write your answers from smallest to largest. So first you do what was happening at -2? Absolute maximum. So you write absolute maximum here, and then you put coordinates here. And then what you do next? Absolute minimum. Okay, now you could say absolute minimum, but you could also say relative minimum. So I'm not sure what they want. I mean, I'm pretty sure they want absolute minimum, but it's also a relative minimum, right? Because, yeah, right? It's a relative minimum also, but I guess they want absolute minimum. And then you'd write the next one is what? Absolute maximum. Okay? Okay, so what about this one? What's the domain here? Negative infinity to 0. So we try and attack this the same way. So what does that mean? We want to look for the critical points, which means what? Where the derivative is 0, and the singular points, right? We want to find the critical points, so that means these two. So we want to find the stationary points, that's where the derivative is 0. We also want to find out if the derivative is not defined anywhere. Okay, and then we check the endpoints. So, what do we have to do here? What's the derivative? Well, actually, we just did this derivative, right? We just did this part, so now we just have to add on this one. So what is the derivative of this? 2/3, right? So is the derivative ever going to be 0? What was it again? 1 over something. I'm not sure. What do you think?
It's hard to judge.
What was the derivative again? What is the derivative of this? It's x plus 1 to the negative, oh, this is different, I'm sorry. This is x plus 1 to the negative 1/3, right? X plus 1 to the negative 1/3, isn't that right? Oh, thank you, right. But it is negative 1/3, right?
Yes.
Yeah, negative 1/3. And then we have to add on plus 2/3, right? And then we're asking, is that equal to 0 ever? So we can write, let's see, there's a 2/3 in both places, right? So what should we do now? I guess 2/3 times, is this going to help? I'm not sure. X plus 1 to the negative 1/3 plus 1 equals 0. Is that going to help or not help? Maybe. So we can ignore the 2/3. Right? Okay, so now we have what? 1 over x plus 1 to the what? Cube root of that, right? To the 1/3 plus 1 equals 0. So that gives us, tell me if I'm making a mistake. Okay, is that going to work? It seems like that might give you, there might be solutions to that. Okay, how do we solve that? So bring that up and bring that over. So that's x plus, wait, how do we solve that? X plus 1 to the 1/3. That's negative, no, we don't want that. Cube everything, cube everything, then what happens? You get x plus 1 over equals negative 1. Right, if we cube this and we cube that. So what about that? Does that have a solution? That gives me x plus 1 equals negative 1, is that right? So if x equals negative 2, does that work now? Yeah, no. Negative 2. If x equals negative 2, then this equals that. So there is a place where the derivative is 0, I think. Right? I'm not sure. I guess we have to go back and check, make sure that the derivative is actually 0 at negative 2. Because we cubed. I forget if we're allowed to do that. I forget if we introduce extra solutions. So anyway, we should go back and put in, well, I guess we can do it now. So if I put in negative 2 here, what do I get? It doesn't look good. If I put in negative 2, oh wait, if I put in negative 2, yeah. I get the cube root of negative 1. Yeah, I guess it works. So there is a place. Where is it? At negative 2. So at negative 2, the derivative is 0, maybe, if we didn't make a mistake. So and that's in the domain. So, okay, then what else do we have to check? What else do we have to check? We usually should check the endpoints, right? The endpoints of the, is there any place where this is not defined? Any place where the derivative is not defined? Yeah, when x is negative 1, the derivative is not defined, right? So that's a singular point. So we should also check there. So where do we have to check? We have to check 0, here, and we have to think about what's happening all the way to the left. So, okay, we know how to check here, here, and here. Here we just put those values into the function, not into the derivative, into the function to get the height. Okay, and then, but then, how do we check? What do we do for negative infinity? So that means we want to ask this question. What's the name of this function? K. So we're talking about K. And we're wondering, like, at negative infinity, right? What's it look like there? So basically, we want to ask this. That. So that's asking what's happening as x gets more and more negative. How can we do that? So what was the original K? What's the original K? It is 2/3 x plus x plus 1 to the 2/3. This is the K. So what happens to this, or can we think about what happens to this as x gets larger and larger in the negative direction? So this goes to negative infinity, right? That goes to negative infinity. What about this? That's interesting, right? What happens to that? -1, really? When x gets, so basically we're looking at something like this, right? I mean, we can't really write that, but I mean, the 1 doesn't affect anything, right? So basically just negative infinity, or something really big in the negative direction. And then we're squaring it and taking the cube root. So what does that do? No, I think taking the cube root, what does that do? That makes it smaller, but it doesn't, you know, if I take the cube root of 1,000,000, can I do that? Yeah. What's the cube root of 1,000,000? I think it's, isn't it? 1,000. Sorry, 1,000. No, not 1,000. 100. Right? 100. Right? 100 cubed is 1,000,000, right? So the cube root of 1,000,000 is 100. The cube root of bigger than 1,000,000 is going to be bigger than this. Bigger than 100, right? But it's still getting bigger, it's just not getting bigger that quickly. Right? So this, as what goes inside gets bigger, the cube root still gets bigger, infinitely bigger, just not as quickly as the original number does. But still, you can make it as big as you want. And then squaring that just makes it even bigger. So this number is just getting bigger and bigger and bigger. Or rather, this thing is just getting bigger and bigger and bigger, but it's negative. What does that mean? So and that doesn't matter, right? Because we're talking about negative numbers, putting negative numbers inside, it just becomes a large negative number. Okay, so this part becomes a large negative number, and this is also a large negative number, so together they become super large negative numbers. So it's going to minus infinity, right? The whole thing is getting bigger and bigger in the negative direction. So the height of this function, if we think about it, is somehow, I don't know what it looks like over here, but somehow it's going down. Right? As x gets more and more negative, it goes more and more negative. So it's dropping down infinitely. Okay, so what did we find? We have to check 0, we have to check -1, we have to check -2, and then at infinity, at negative infinity, it's just going down forever. So there's no absolute minimum. Right? There is no absolute minimum because it just gets worse and worse. Okay, then we just have to check the rest of the points to see if there's any absolute maximum and if there's any local minimum or maximum. So how do we do that? So here's k. So we can ignore negative infinity, so we want to check when x is -2, -1, and 0. Right? So, how about that? When x is -2, what do we get? When x is -2, what do you get? 2/3 times -2 plus -2 plus 1 to the 2/3. Right? Is that right? Do I have the right function? Hope so. Okay, so what does that give me? -4/3 plus 1 to the 2/3. Okay, so this is when x equals